Welcome to this predicted paper from onmaths. This paper represents the best guess for the upcoming exams. Please use this paper in addition to your other revision. You can complete a unique version of this paper by going to our onmaths site. Onmaths is full of free content to help you prepare for your exams, such as topic-based papers, demon questions, and mini mocks. If you like what we do, please consider subscribing. We're asked to draw a tree diagram for the probabilities, so we're going to start with our first choice, and our first choice comes from bag A, and so we're just going to show that. And our choice will be between a red and a green marble. It's from bag A. Next choice, well, if it is a red marble, Ellie will stop selecting, so we can stop the red. But if it's green, she will continue. So we're going to do another one from the green. And again, she can pick a red or green, this time from bag B. Again, if she selects a red marble, she stops. So we're going to continue from the green. And we're going to have our two outcomes, which will be red and green from bag C. Putting in the probabilities, well, there's 1 red and 9 green in bag A, so it would be 1 over 10 for a probability of selecting a red, and 9 over 10. Next one will be 1 over 4, 1/4, and then a green will be 3/4, and then the last one will be 1 over 3, 1/3 for a red, and 2/3 for a green. In probability, when we are asked to find the probability of 3 green marbles, or 3 of anything, it's more useful to think of it as 1 and 1 and 1. So we're looking for the probability of a green and the word and in probability means times, another green, and another green. So we go back to our tree diagram from part A. So we're looking for the probability of the first green, the second green, and the third green. So that's going to be 9 over 10. Times 3 over 4 times 2 over 3, and that will be 9 over 20. In this question, we're asked to find the probability that Ellie will select at least 1 marble of each colour. So if we go back to our tree diagram from part A, we can see if a red is selected first, then a green can never be selected, so that's not going to be one of the options. If a green is selected and then a red, that's 1 of each colour, so that's one possibility. Or a green, then a green, and then a red. So those are our two options there. So it's green and a red, or green and a green and a red. So let's put that down. So probability of a green and a red, or, and in probability we use plus for or, green and a green and red. So let's change these for the actual probabilities. So it'd be 9 over 10 times 1/4, and then we're going to add that to 9 over 10, then another green, so 3/4, then 1/3, and the answer to that will be 9 over 20. In this question, we're told that Ellie has selected a red marble, and we're asked to find the probability she'll have selected it from bag B. So looking at our tree diagram, we know that either, well, the possibilities are that she picked a red straight away, she picked a green then a red, or she selected a green, and then a red. So let's work out all of those probabilities, because we know that she hasn't picked a green and a green and a green. And actually, we could take that probability away from 1 to find the total probabilities that are in play. I'm not going to do that just for simplicity, well, for lack of simplicity probably. So I'm going to find the selection of a red first, or, which is a plus, the probability that she got a green and then a red, or probability of a green and then a red. So that will be in total 1/10 plus 9 over 40 plus 9 over 40, which would be 11 over 20. So all the probabilities that are in play are 11 over 20. So it's no longer going to be out of 1 because we said that it cannot be a green and a green and a green. Now we're looking for the probability that she will select the red from bag B, which means it will be green and then red. So we're going to work out the probability of a green and a red, and that's going to be 9 over 40, so it will be 9 over 10 times 1 over 4. Okay, now with this, with all probabilities, we look for the one that we are looking for, which is that 9 over 40, and we put it over the total amount. So normally it's over 1 because all of them add up to 1, but because we are discounting the green, 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 it's going to be 11 over 20. So we're going to put that over 11 over 20. So we're doing 9 over 40 divided by 11 over 20, which is going to give us 9 over 22. Looking at the scatter graph, the data is going downwards. So we say that this is going to be a negative correlation. We're already told that the x-axis is the daily mean temperature, so you just need to have a familiarity with the large data set, and you can find it online and just look through it and you'll find that the variable is going to be rainfall. And it asks us to state the units, so it is measured in millimeters. So in this question we have to come up with a hypothesis, and we also need to find the critical value, and then we need to carry out the test. So we're told that Carl believes there is a correlation between the two variables. Now that's really important. He's not saying that he thinks it's a positive or a negative correlation, that there just is a correlation. So we can do the hypothesis quite straightforwardly. The null hypothesis, now remember the null hypothesis is that nothing's happening, there's nothing special here, just two random variables. And so we're going to say that rho is equal to 0, that there is no correlation. But the alternative hypothesis, the one we're trying to prove, is that there is a correlation. So rho is not equal to 0. So it's either going to be a positive correlation, negative correlation, just going to be interesting. So we go first of all find the critical value. And we're going to do that using the tables. So we're going to look up instead of 5%, because it's a two-tailed test, we're going to look up 2.5%. So we're going to look up 0.025 in the tables. And the sample size, the n, is going to be 30. So n is going to be 30. And when we look that up, we find that the critical value is 0.3610. And we know that that's either positive or negative. So the critical area is going to be that r is either going to be greater than 0.361, or that r is going to be less than minus 0.361. Now looking at the value of r that he's obtained, we can see that minus 0.482 is less than minus 0.361. So we can say that there is evidence to reject the null hypothesis. So we can say that r is less than minus 0.361, so significant result. So we've got a significant result, and there is evidence of a correlation between the variables. Now in the exam, just make sure you state the variables. So between daily total sunshine and daily maximum relative humidity. So we know that there's going to be a negative correlation between daily maximum relative humidity and the number of hours of sunshine. So looking at the daily maximum relative humidity, it's quite high, 96%, it's actually very high. So therefore we would expect a lower than average amount of average hours of sunshine. So we just say lower than average hours of sunshine, because there's that negative correlation. We can see that Chelsea's modelling this experiment with the binomial distribution, and the binomial distribution has 4 conditions. The first is that there are 2 possible outcomes, so it's either a win or a loss, or a success or failure. That there are a fixed amount of trials, because we need to feed in n, that there is a fixed probability of success, and that the trials are independent, so the probability of success is constant. So the 2 that I would use for this are the probability of a hit is constant, and that the throws are independent. Now, independent is a really key word to use here. So it basically means that each throw won't affect the probability of the next throw. Now, this could be a problem, because you'd think that as you throw the darts, you'll get better at it, or you might get tired and you might get worse at it. So we're going to be using Chelsea's model, which is the binomial distribution, to work out the probability that h is greater than or equal to 4. So we're just going to copy down the binomial distribution from part A, so it's 10 and 0.35. Now, we're not going to work out the probability that h is greater than or equal to 4. The way we do it is we always make it less than or equal to, and so we can work out that if we take away the probability that h is less than or equal to 3 from 1, it'll give us the same amount. And we're going to use the calculator for that, so I'm just going to bring up the calculator, and we're going to do using this calculator, and your calculator might be slightly different, but you press the menu button, and then we're going to press 7, and the binomial CD is not there, so we're going to press down, and it's the top one there, so we're going to press 1. We want to do variable, so number 2. So these are the 3 numbers we need to input. The first number is this part here, the 3, and then press equals. The n is the first number in the brackets, so 10 equals, and then obviously the probability at the bottom, 0.35. And then equals, and then when we're ready for the answer, we just press equals again. And so that will say it's 0.5138, blah, blah, blah. Now the problem is we can't work out 1 minus that in this mode. We need to switch the mode back to normal, so menu and 1. But what the calculator will do is remember what that number is. So we can do 1 minus and then answer, and that will give us the answer. So that's 0. And to 3 significant figures will be 0.486. This question is actually asking a very simple question, but the way it's asking it means we've got to kind of think a little bit, because it's setting the random variable f as the number of the throw on which the dart first hits the target. And so what this is saying is that the child first hits the target on the 5th throw. And then in probability, we want to write that out in a way we can then calculate the answer. So instead of them getting it for the first time on the 5th row, we're going to say, well, they're going to miss the first one, and in probability that means times, miss the second one, and miss the third one, and miss the fourth one, and then hit the 5th one. Okay, so that probability of a miss we can work out because it's just 1 minus 0.35, which is the probability of a hit. So that's going to be 0.65, and we're timesing it by 0.65 times 0.65 times 0.65, so we can just do that to the power of 4, and then times the probability of a hit, so that's 0.35. And that is going to equal 0.0625 to 3 significant figures. The key part of this question is that no child will need more than 10 throws. So we know that if we add up each of the probabilities from 1 to 10, then it must equal 1 because no child will need more than 10 throws. So we're going to do a quick table, and this is going to take a while, but it's worth 4 marks, so it's definitely worth spending a bit of time over. And we're going to have n from 1, 2, 3, 4, 5 for each of the throws, and the probability that they get a hit. So the first one, we're just going to do 0.01 plus, and it will be n minus 1, so that's going to be 0. So it's just going to be 0. And then the next one will be 0.01 plus 2 take away 1, which is 1, so it would just be an alpha. And then 0.01 plus 2 alpha, 0.01 plus 3 alpha, 0.01 plus 4 alpha, 0.01 plus 5 alpha, and you can kind of see what's happening here. And I don't know, if you can do this quickly, it's probably worth writing all these out. Because I find sometimes when I try and do things in my head, especially under the pressure of the exam, you can make mistakes. So we can see here that we've got 10 lots of 0.1s. So obviously 10 lots of that would be 0.01. So 10 lots of that would be 0.1 when we add those all together. And here we're just going to count up the alphas, and that's going to be 45 alphas. And we already know that that's going to equal 1 because, as I said, no child will need more than 10 throws. So we're just going to put our lines in and solve this. So we're going to take away 0.1 both sides. And we get 45 alpha equals 0.9. And we're going to divide by 45 both sides. So alpha will be 0.9 divided by 45, which will be 1 over 50. So Darren's model is actually pretty straightforward now that we know what alpha is, because it just tells us that for when f equals 8, it's going to be 0.01 plus, and then we're going to do 8 minus the 1, and we know what alpha is, it's going to be 1 over 50. And so we can get all of that information from part D. So when you type that in, you get 0.150 when given to 3 significant figures. So we discussed already that Chelsea's model assumes that the probability will remain constant. But if we look at Darren's model again, we can see that the probability is increasing each time because we're multiplying the alpha by a larger and larger amount. So the biggest thing is that, and we can write this down, so Chelsea's model assumes that the probability of a hit is constant, and then we said Darren's model assumes the probability of a hit increases with each attempt. So the first thing I want to do is draw a Venn diagram, because I find it a lot easier to figure out what's going on. And we've got variables, or we've got the A and B, so we'll have A and B. And we can see that there's an A and B, so there's going to be an overlap between the two. And let's just label it A and B. Now we can see straight away that the probability of A and B is 0.17. So we can put that in. If the probability of the overlap is 0.17 and the total probability of A is 0.42, we can just do 0.42 take away 0.17, and that would be 0.25. And then same with probability of B. We just take that away from the 0.17 away from the 0.53, and that will leave 0.36. And obviously they all need to add up to 1, so we're just going to take away the 3 decimals away from 1, and you get 0.22. So looking at what we're asked for the probability of not A given not B. So we know that B has not been picked. So the only probabilities that are still in play are these two, the 0.25 and the 0.22, because the others are in B. We know that they cannot happen. And so we're looking for the probability of not A. Now not A is this one here. And so what we're going to do is we're going to do probability of not A given not B is going to be the one we're looking for, which is the 0.22, over the total amount of probability. So that's going to be the 0.22 plus the 0.25. And that's just going to be 22 over 47. So to work out the probability of two independent events, such as getting a 1 on a dice, which would be 1 over 6, and getting a heads on a coin will be a half, we just multiply them together. Okay, so that's basic probability there. So if these are independent, we would expect just to be able to multiply them together, and that will give us the probability of A and B. So let's do that. So the probability of A is 0.42, probability of B is 0.53. So we're going to do 0.42 times 0.53, and that's going to give us 0.2226. But if we have a look back, we can see that the probability is 0.17, which is not the same as we've got. So 0.2226 is not 0.17, and so therefore they cannot be independent. So there's a lot to unpack with this question. The first thing we're going to notice is that events A and C are mutually exclusive. So we can actually draw the Venn diagram now, because they're mutually exclusive, it means they won't overlap. So we can do the A and B as we did for part A, and this time we just add another event to it. So we've got A, B, and C. Now if we look back at part A, the probabilities here won't change. So the 0.25 and 0.17 will still be there. So 0.25 and 0.17. Next thing we notice is that B and C are independent. So we can work out the probability of B and C by just multiplying the probability of B with the probability of C. And so we're going to do the 0.53 probability of B times the 0.1 for C, and that's going to give us 0.053. So this middle bit here is going to be 0.053. Take that away from the 0.1, and that will give us the remaining part of C. take both of those away from the 0.53, and that will leave us with 0.307, and take all 5 of those away from 1, you get 0.173. So this is asking us to find the probability of not B or C. And so we're just going to rewrite that. So we've got B or C, not. And we're just going to do 1 minus the probability of B or C. So looking back, we can just work out the probability of B and then add on the C. Remember, or just means everything that's in B or C or both. So the probability of B is 0.53. And the bit remaining is the 0.047. And so when you take those away, or when you add them, sorry, you get 0.577. Take that away from 1 and you get 0.423. So we're going to approach this question by just putting the numbers into the calculator and letting the calculator work out what the answer is. Pretty straightforward. So we're going to start by clicking menu, and we're going to go to number 7. And we want to go to number 2, which is the normal CD. And we're going to put in the lower amount, which is 10, because it says will last longer than 10 hours. The upper amount, we're just going to put a really large number. So what you can do is do 9 times 10 to the power of 99, or just put loads of 9s in. Essentially what is going to happen is the normal distribution is a bell curve, so the probabilities are very, very tiny to the far right of the graph. So we just want to put a number that's big enough that it's not going to affect our answer. Then we're going to have a look at the question for the standard deviation. So it says it's 5. And then equals, and then we need the mean, which it says it's 12. And then just press equals, and so the probability that L is greater than 10, L being the randomly selected battery that will charge, is going to equal the 0.655 to 3 significant figures. So for this question, we're just going to start by focusing on one battery, and we're essentially finding the probability of L being greater than 14, but given that L is greater than 10. So we know that it's already lasted 10 hours. And we know for that we're going to work out the probability that L is greater than 14 and divide it by the probability that L has lasted for more than 10 hours. Okay, so we're going to use the same process as part A on the calculator. I'm not going to show it, but if you're not quite sure, just have a look at the answer to part A. And I'm not going to round them yet. I'm just going to store them in the calculator. And that should give us 0.5257. But that was only for one battery. We're going to work out the probability for one battery and one battery and one battery and one battery, so 4 in total, and we're going to multiply them together for that. So we're going to do 0.5257 blah 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 times by itself times by itself times by itself times by itself, so to the power of 4, and that'll give us 0.0763 blah blah blah, and to 3 decimal places will be 0.076 to 3 decimal places. So we're going to start by looking at the new batteries. So we need to find out the probability that they're going to last for more than 4 hours. And we're just going to use the same method as part A to find that that's 0.945. And blah, blah, blah. And now we're going to use our answer to part B, specifically this one, because that shows the probability that the batteries we didn't replace will last. And so we're going to look at the probability of 2 of those batteries and 2 of these batteries. And so we're going to do 0.5257 blah 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 times by itself, and then times it by these 2 batteries here. And then when we do that, we get 0.247 when rounded to 3 decimal places, which is the number in the question. So Jay believes that the lifetime of the batteries was more than 12 hours, and he's done an experiment with a sample of 20. And we're asked to state the hypothesis and test his belief with a 5% level of significance. So let's start by doing the null hypothesis, as we always do. And this is that the population mean is 12, because that's what we're told is the default position. His alternative hypothesis, what he's trying to prove, is that it's more than 12 hours. Now this is obviously one-tailed, so the 5% level of significance we're just looking for 0.05. So it's not going to be a two-tailed test, because it's that we're looking for it more than 12 hours, not different to 12 hours. Okay, so we're going to do the distribution. So we're going to have a look at the sample mean. And the way of doing this is the mean will just be the same, so it would just be the 12. And this is assuming that the null hypothesis is correct. And it's just a little formula here, and we get the standard deviation, put that over the square root of n, which would be 20, and that will give us the standard deviation. Obviously, we should write it as a variance. Okay, so using this normal distribution, we're going to find the probability that the sample mean is greater than 13.8. And what we're doing here is, if we just do a quick normal distribution or bell curve, we're trying to see whether that 13.8, and hang on, let me just put in the values actually. So the mean is 12, and the standard deviation is 5 over root 20. And that 13.8 is somewhere here. But we're looking to see whether it is within the range that we're saying is very, very unlikely down to chance, which is this kind of 5% range. And if it's on this side, then we start being happy because we've shown something. If it's on this side, then we start being less happy because we haven't shown anything, because we say that that's probably down to chance. So when we put that into the calculator, such as in part A, we get the answer of 0.0537. And we're starting to be a bit sad because when we round that to 3 decimal places, or we can just keep it as it is, it's up to you, we see that that's bigger than 0.05. So unfortunately that is on this side, on the left hand side of the line. So we can say that there is not enough evidence to suggest that the population mean is more than 12.
You can complete a unique version of this paper by going to our onmaths site. onmaths is full of free content to help you prepare for your exams, such as topic-based papers, demon questions and mini mocks. If you like what we do, please consider subscribing.